such a perfect segue into what I'm going to talk about, in particular, those last two questions about removal or functioning and of the ponds versus more of a wetland system. So I'm excited that I was placed right after them. So I'm calling from Vermont. The work I'm going to talk to you about is based in Vermont, so a cold climate setting, different from Florida. But I've been interested in the way Florida manages stormwater ponds, in particular because they are ubiquitous, and it seems like they're managed even as a part of the landscape in a different way than they are certainly in the Northeast. And a friend and colleague of mine, Casey McMahon, who is living down in Florida and is involved in the yachting and water sports community, has really gotten me more interested in some of the particular water quality concerns in Florida. So even though I'm far flung, I think we have some overlap. So I'm enjoying the conference so far. Next slide, we'll just dive in. So I just really quickly overview, which I'm sure you're all pretty familiar with, but just wanted to set the stage about the problem with stormwater. So there's sort of these two characteristics. One is that we have too much quantity, it's too much volume for little streams, and the other being that the water quality entering the streams is of a low quality. Next slide. And so really, like this pre-development condition versus a development condition can lead to up to 400 times greater flow in urban streams than the pre-development condition, and developed lands can be exporting 5 to 20 times more phosphorus than undeveloped landscapes. Now, the idea that was instituted based on the impervious cover model in the 1980s is that if we manage for the volume, we can improve the quality of the water in the stream. And that idea has really carried us through all of our permitting around stormwater for the past 40 years. We've been managing for volume only, thinking that if you can control the volume challenges, you can improve water quality. Next slide. And the way we've done that has been through these stormwater treatment controls, wet retention ponds being the most common, but other ones like dry detention basins, infiltration chambers, filter strips, gravel wetlands, bioretention. Those ones that are outlined in green are sort of what we consider green stormwater controls or green infrastructure. But those retention ponds are really more common than any of the others, and they specifically target the treatment of the volume concerns more than the quality of the water. And that's also going to be the topic of what I talk about today. Next slide. So stormwater ponds are really good at managing volume because they're essentially just bathtubs. And in Vermont, I'm not sure what this is in Florida, but in Vermont, ponds are regulated to remove 80% total suspended solids and 40% of total phosphorus. But this Center for Watershed Protection study, just kind of a conglomeration of a bunch of different studies from 2007, analyzes what they actually are performing at in the field. And you can see the box kind of outlines the total phosphorus and total dissolved phosphorus removal rates from all the studies that were included here. And that lower bar, that lower gray bar, that is at -50. So anything that's falling below that zero line, which is above the gray bar, indicates that there's actually loading of the pollutant. So the total dissolved phosphorus from some of these ponds is actually greater leaving the pond than it is coming into the pond. And so if we're assuming that ponds are removing 40%, it's not really clear from these data that they're doing that. Next slide. So managing for volume doesn't seem to really have solved the problem. Our water quality in streams remains poor across the country, even where we're implementing best management practices. It's not really changing the impact on macroinvertebrate communities to pre-development conditions, which is a common measure of urban runoff impacts. And the stormwater ponds, which are being used to store and slowly discharge the stormwater volume while settling out the particles, they may be doing that, but they may actually be doing something more like cycling nutrients within the pond in a natural pond system. Next slide, please. So why is that important? Well, it's important because it may be that design is influencing pond performance in a way that we didn't really understand, or also just that ponds aren't functioning for water quality in the way that we initially had thought. So they're really common. As I said, the most common stormwater control structure used in the US. And if there are factors that we can influence performance based on design, then we should be using those up front. And most importantly, if what we're finding is that stormwater ponds actually have an alternative effect, meaning that they could be loading more of this dissolved phosphorus, which is this more bioavailable form of phosphorus, that could actually be negating some of our efforts. Next slide, please. So the research I'm going to talk to you about today is looking at stormwater pond form and function. So seeing if stormwater ponds differ in their water quality. And this is internal water quality, not inflow outflow. So just seeing what are the morphometric differences, what are the drainage area differences of the pond themselves, and then looking a little bit about the phosphorus released from the sediment into the water column, and if there's any overlap between these design characteristics and the performance of the ponds. And then the second part that I'm going to talk to you about is this modifiers to existing stormwater ponds using floating treatment wetlands, specifically in cold climates. So that'll be the second part. Next slide, please. So really quickly, I'll just talk about what we measured in this in the stormwater pond study. So it's 7 permitted stormwater ponds, all in Vermont, in the greater Burlington area. So it's our largest city in northern Vermont. We looked at temperature throughout the water column to determine stratification intensity, so at 3 depths over the course of a summer season. So it's from May till September, I believe. We also collected water grab samples at the surface and the sediment water interface over 6 periods, dry and wet periods, 3 of each. Analyzed those for total phosphorus and soluble reactive phosphorus. So that's the inorganic portion of the total dissolved. Then we took sediment grab samples and analyzed those for percent moisture, organic material, physical characteristics like sand, silt, clay, and the chemical constituents. We also looked at reactive iron as a way to tell about how the phosphorus might be binding to certain other chemical constituents. And then we looked at the plant community coverage. Another thing we did, which I'm not really going to get into, but if you're interested, I'd be happy to talk to you about it after, is we used peepers to look at the relationship between the phosphorus in the sediment and right above the sediment water interface to see if we could measure basically pumping action of phosphorus from the sediments into the overlying water column. And we have some interesting results from that as well. Next slide, please. Great. So this is just a couple of photos of us out on the stormwater ponds collecting samples. You'll note that, so the challenging thing about trying to get the sediment water interface and at the surface of the water column, you want to be really careful not to be churning up the water. So that's why we have this little string attachment. So we would slowly glide into the center and the deepest part of the ponds in order to collect those samples. Next slide. Yeah, just one more. Perfect. So this is an overview of the morphometric characteristics of each of the ponds. And so you'll see there's variability. The top is the cross-section through the deepest section of the pond at a 90-degree angle between the inlet and the outlet. And so the ponds are really different in size, which is the way, you know, ponds meet the needs of the development. So that's not surprising. So they're different depths and they're wildly different shapes and sizes across the board. None of the ponds that we looked at were deeper than 1.5 meters, but certainly some are. It just so happened that all the ponds that we could find within the most dense areas that were also permitted post-2002 were not more than 1.5 meters deep. And next slide. So the first thing I want to show you is this stratification intensity. So we calculated the intensity of stratification based on the temperatures at the surface and the sediment water interface. And what we found is that some ponds stratify, and some of them don't. And right off the bat, you might think that would be related to depth. And the deepest pond, which was pond 7, did stratify more times than any of the others. But the shallowest pond actually had the most intense stratification event. And so there definitely are more things at play than just depth here. It could be salinity. We're in a cold climate, so salt is added to the road. So sometimes these stormwater ponds can have pretty high conductivity, and so that can influence the resistance to mixing. It can also be the fetch, location on the landscape, vegetation coverage, that kind of thing. But ponds are definitely stratifying, and when ponds are designed, they're designed as well-mixed reactors, assuming that they don't stratify and that they're mixing completely. And what we're finding is that that is not actually true. And that has major implications for nutrient cycling from sediment. Next slide. So this one, this is an outline of the phosphorus in the sediment, so the sediment characteristics. So the total bar, the full size of each of the bars, shows the total phosphorus, and then we fraction that phosphorus into organic and inorganic. And the organic portion we further fractioned into potentially mineralizable phosphorus. So that's done by an anaerobic core that then we measure pre and post an anaerobic period to see how much of that organic P will mineralize and become available. And so what you see is that pond 3 had the highest total amounts. This is going to be important later, so remember this, that pond 3 had the most overall total P content, but that the fraction of the organic P in pond 3 that was potentially mineralizable is very small. Whereas in a pond like 2 or in 5, the fraction of the organic phosphorus that's potentially mineralizable is much higher. So that's important. Perfect. Yeah, thank you for that. It was perfectly timed. And so when we lay that over the constituent manganese and iron in those sediments, we did that to look at those are common the manganese and iron will bind with the phosphorus, and they're important because the species are redox sensitive, meaning that they'll be influenced by reducing conditions at the sediment water interface. So when oxygen is depleted, those species will be likely to release that phosphorus into the overlying water column. And so you can see in pond 3, where we had the most total phosphorus and the least amount of potentially mineralizable phosphorus, it also had the highest manganese and iron content. So next slide. And I'll circle back to what we think that means in just a minute. So then we looked at the ecological community structure. So they were really variable, the ponds and their ecological community makeup. So some were filled with algae and floating plants, like pond 6, for instance, and others had none or very little, like ponds 2 and ponds 5. And similarly, some ponds, like pond 4, didn't have any rooted macrophytes at all within the pond area. And for the purposes of this study, just to clarify, floating plants and algae were lumped together in a % coverage estimation because they represent this more labile form of phosphorus in the pond than the rooted varieties. And what we were trying to get at is, how is the phosphorus being used in the ponds to build biomass? And is it being used in a form that can be exported as rain events move through? So you can see there's a lot of variability between ponds. So the thing to note here, just remember, is that pond 3 here has a lot of those potentially movable plant types, and less, pond 3 has a lot of the rooted, not movable plant types, and not a lot of the algae and floating plants, which could be moved out of the pond. Pond 5 has no algae and floating plants, but a lot of the rooted macrophytes. And next slide. So if you remember back to how pond 3 had the highest total phosphorus in the sediment and pond 7 had the lowest, here you can see this is the phosphorus levels in the water column, and the white boxes are the TP at the surface, and those little speckled boxes are the TP at the sediment water interface. You can see that the amount of phosphorus in the sediment doesn't seem to have impacted the P content in the water. But if you remember how pond 6 had the highest percentage of algae and floating plants, and 5 and 2 had the lowest, it looks like there might be something in there. So 5 and 2 had the lowest floating plant components, and they also have the lowest total phosphorus in the water column. Pond 6 had the highest, and it has a lot of phosphorus in the water column. So the question really is that driven by external factors or internal factors, or some combination of those things? Next slide, please. So, so to understand that, we looked at what's the correlation to the drainage area and the pond design. And so here, the fetch and the total drainage area, so not the impervious cover or surface area, which is what ponds are designed based on, are really linked to water quality. And interestingly, these features differ between the surface and the sediment water interface of the ponds. The total drainage area was strongly correlated with sediment water interface TP in both dry and wet periods. But fetch didn't strongly correlate to phosphorus at the surface in dry periods. So what that means is that we think that's indicating that there's something other than design or watershed characteristics that's influencing phosphorus in the water column, something maybe like internal release from sediments. Next slide. So the water quality correlation to sediment characteristics, so the only sediment characteristic, and remember we did like a full chemistry analysis, the only sediment characteristics that are directly linked to water quality in these ponds is reactive iron. The total phosphorus and the inorganic phosphorus in the sediment are correlated with iron and manganese because they're binders of phosphorus and they're redox sensitive, meaning that the bind is broken and the inorganic phosphorus is released when the oxygen is reduced in the sediments due to microbial activity. So all of these things are kind of coming together. If you have ponds that are stratifying, you're getting reducing conditions of the sediment water interface. The chemical constituents of your sediments are either binding or not binding, or being sensitive to release or not sensitive to release, and it'll really drive what your overlying water column water quality is. Next slide. So this is the last slide of results I'm going to show for this. And this is the water quality correlation to the sediment characteristics in the thermal structure. Oh wait, it looks like, hang on, go one more for me. Yeah, that's it, perfect. So the RTRM, this is the thermal structure. And then the algae and floating plants. So the algae and floating plants in the water column is strongly correlating with total phosphorus at the sediment water interface. And that makes sense because the mats of algae represent this transient pool of phosphorus. So it's growing, it's settling to the bottom, it's dying, it's releasing total phosphorus back into the water column. And it suggests that the ponds with lots of algae are prone to this higher mobile TP in the water column, either as like particulate inorganic phosphorus, like bodies of plants, or as the solubilized inorganic phosphorus. Regardless, neither is good in a treatment pond because it is leading to this export to natural waters. And even though depth is strongly correlated with the thermal resistance to mixing, it didn't directly influence water quality. So that was a little bit of a surprise to us. Next slide, please. Perfect. So the conclusions from this one is that pond design should consider internal dynamics as much as external loading, like maximizing fetch, which can help with turnover, even if you're having thermal resistance. And the total drainage area, more than impervious area, may be driving the nutrient levels in ponds, which is not how they're necessarily designed. There's this other thing that is interesting, which is that the sediment or the pond liner soil chemistry is influencing phosphorus exchange between the sediment and the water column in the overlying water column. And there's maybe some interesting discussions to be had about using native soils versus pond liners in decisions around the chemistry and how that might improve or not the performance. We're also thinking that like design that encourages rooted macrophytes growth over like the algae and floating plants, so a shallower step design could improve water quality. So depth plays a role in that. There's definitely more data needed, like measurement of biomass instead of the qualitative one that we had done. And then additional influencing factors like I had said, the salt concentrations from de-icing, which I imagine would not be much of an issue in Florida. All right, next slide, please. Thanks. So what are some existing pond options? Oh, it looks like your slide, you can, yeah, there you go. I just have a couple of, you could just kind of click through. There's just a few pictures here. So seeing what we knew about stormwater pond function and some of the ways that stormwater ponds weren't functioning, the next part of the study looked at existing pond modifications that could potentially improve pond performance. So we looked at floating treatment wetlands. Next slide. So floating treatment wetlands and stormwater ponds, you may be aware it's been approved by the Chesapeake Bay for stormwater pond improvement, and it kind of looks like this, what has been approved. So it's based on raft coverage in pond. If you cover the pond by 30% surface coverage, you can expect 2.5% incremental increase in TN removal performance of 2.5, and up to 7% increased removal in TSS. The important thing to know is it's approved in some places, but there's still so much we don't know about how they work and if they work and where they work and how they work best. So we're just trying to understand a little bit more about how they work in cold climates and if they're working as we think. Next slide. So this is just the second part of the study, which I'm going to kind of zoom through, but the questions really are modifiers to existing stormwater ponds, and can they be used to improve stormwater pollutant performance, and if some macrophytes work better than others in cold climates based on survival biomass. But this could be done anywhere. I mean, the question really is, do some macrophytes work better in floating treatment wetlands? Okay, next slide. So here's just a little bit about the study site. It's a 10-acre watershed area, surface area of about 213 square meters, discharged to a local water body that's impaired. And next slide, next slide. Yeah, and then just flip through again. Sorry, I have a couple zoomed in here, and then you can, yeah, perfect. So here's the wetland design and layout. So the figure on the left is the simplified version of the plan view of the total pond. And then all those little squares on there are each of our floating treatment wetlands. They each had a different plant species on them. And then the figure on the right is a zoom in of one of the wetland pairs. And so we paired each of them. Each one of those would have a different species on it. Next slide. There's a little cross view of what it looks like. So they're anchored to the bottom of the pond. They float on the top. Plant roots grow down into the water column. The idea being it increases entrapment, flocculation, sedimentation. Next slide. And here's just some pictures. So we built these ourselves. We use this polyflow biological filter material, bought in big rolls, cut them out. You can do next slide. Filled them with some foam. Next slide. There's pouring the foam, cut the little holes in them. Next slide. Bought some plants. Next slide. Put them in the water column. We had the pond drawn down for the event to make it a little bit easier to put in. Next slide. This is them right after they were installed. The pond's still low. Next slide. This is them in the middle of the summer. So you see the plants are growing up, looking like a hazy day. A little bit. Next slide. And here they are yeah, just another picture from the summer, another angle. You can see some of the plants aren't doing so hot. Next slide. And again. And another one, just to see, just so you can get a sense of them growing in over the summer. Next slide. So the first set of results I'm going to show you, this is just going to be brief, but we also looked at the performance of the pond before and after the installation of the floating treatment wetlands, just influent, outfluent with ISCOs. And the thing I just want to point out to you is that the 2015 was before floating treatment wetlands were added. 2017 was after. The highlighted in orange cells show statistical difference between influent and effluent. So, okay, great. TSS is lower going out than it's going in on both years. That's what we would expect. But the thing that I think is really interesting is that TP is not removed, nor is TDP in the pre-floating treatment wetland period, and TP is removed after floating treatment wetlands are installed. That means that the pond is not working to remove total phosphorus, and it's designed to do so. So I see that like we're a little tight on time, so I'm just gonna, I would love if you can just flip through the next couple of slides. You can just kind of flip through and I'll just talk as you flip through them and we'll get to the end. We looked at survivability of plants. Some of them made it through this winter, some of them didn't. We looked at which ones did best in terms of biomass. The long-haired sedge did the best. We looked at plant, shoot, and root phosphorus content, you know, just to see which ones were different. Again, long-haired sedges did the best. We also looked at root architecture using this software called GIA Roots. This is free software to see which ones had the most surface area coverage. And then the big punchline is that this long-haired sedge, Carriage Camosa, did the best. And I will take any questions you have at this point.
Great, thank you, Becky. We have time for just a couple questions here and they're already coming in, so take it away.
All right. Have you done, oh, no, I can't see that one. Have you looked at floating wetland foam to see if it breaks down over time and potentially creates any microplastic pollution? That's a great question. And we haven't, and that is one thing, if I were to do this again, I would probably not use that biological filter material because it is a plastic material and you're putting it in the pond. I didn't really think about the foam even as much, but you're right. You know, some people use that coconut coir and that will biodegrade, so it's probably a better choice. I'd be super interested in doing that if anybody else has some ideas or ways that we could work together, because I think that's a really important question. Do the floating treatment wetlands negatively impact mixing of the water column? Another great question. So one thing that I didn't talk about here is that we did look at dissolved oxygen beneath the stormwater, beneath the floating treatment wetlands before and after their installation, and it does reduce dissolved oxygen beneath the floating treatment wetlands, which is maybe as a result of decreased mixing. It also decreases the temperature though through shading, and so you get kind of like, you know, there's a little bit of a trade-off back and forth, and that's been identified in other studies in the literature. Thank you so much, and that's I think all the time we have for questions, but thanks so much for listening, and I'm looking forward to hearing the rest of the talks.
Thank you so much, Becky. We really appreciate that, and I know everybody had a lot of questions, so feel free to reach out to Becky. Her contact information is in the proceedings document at chnep.org. With that, we're going to go on to the next presenter. Chris Anastasio from the Southwest Florida Water Management District. Take it away, Chris.